is space-time? Well, let's begin at the beginning. We covered the following. We had space, okay? And we looked at existence, and we looked at time in the last couple of weeks, okay? Space and existence are easy. They're static concepts. They fit in a single frame, as you can see there, the yellow bracket there. They fit in a single frame of the universal movie. What's a universal movie? Well, it's a tool. That's what it is. It's a tool where we have location, only location, a static concept in every single frame of that film. So it's like using God's camera, right? And he takes a snapshot of the entire universe. He's outside the universe, right? And like St. Augustine said. So he takes a snapshot of the universe, right? He gives you the snapshot, okay? And so you can see every atom in the universe, every star, every planet, every galaxy. It's there, but static, in a static mode, okay? Because it's just location, distance between all the objects. That's all you have in a single frame, okay? So there you can at least isolate all the static concepts. And there's a couple of them there that we use in physics: object, distance, location, existence. And we have also space, right? It's a static concept. Space is not a thing. Space is that black stuff there. What is that black stuff? Well, it's not a stuff. What it is a synonym of nothing. What is nothing? What's the opposite of something? Something is that which has shape. Nothing is that which doesn't have shape. See how easy it was? They're antonyms. You can use those terms consistently now. On the other hand, you have time. Time is a dynamic concept, and we illustrate that by showing that you need at least two frames of the movie, that the beige bracket on the bottom. So all those concepts there, those are all dynamic concepts. I call them dynamic because they require at least two frames of the universal movie. So we have what? We have space, which is a static concept, and we have time, which is a dynamic concept. How do you merge them? How do you put them together? That's the question. It's like putting together standing still and moving. How do you do that? Right? And that's more or less the situation. That's going to be the trick. How do you achieve that? And apparently, we have people here. We have one fellow who put a comment, okay, and he said the following. He says, "Existence isn't static. We are constantly moving through space, even if we're still sitting still. Our brains are of apes." Oh, okay, that explains that. Okay, maybe that's his family there. Okay, there's no reason for us to understand the truly fundamental nature of time, only what is useful to survive. Yeah, I guess if you live in the jungle, I guess it doesn't matter how you define time, right? It's not important, just survive, right? Talk to any real scientist and they'll admit that the limitations of these concepts, okay? That means they don't know how to define them. That's all it is. I've watched many of Brian Greene's vids. He's a down-to-earth guy and knows that we don't know squat about the universe. Yeah, Brian Greene, I guess he's proud of not knowing anything, and I don't know why this fellow idolizes Brian Greene, because, I mean, why does he follow him? Does he follow him because he knows or because he doesn't know? If he doesn't know, why make him to be such a hero? I mean, he's saying it there. In the 19th century, they had this Know Nothing party in the United States. It lasted for a while, and then it went out, and it looks like these folks have restarted this party. Now they're the Know Nothing party. They know nothing, they're proud of it. Okay? But again, why would anyone idolize a fellow like Brian Greene if he tells you that he doesn't know anything? Okay? You would think it's the other way around, that if you're looking for a physicist or a scientist or whatever, you would look for someone who can explain something and tell you something. But if the guy says, "Oh, by the way, we know nothing," oh, great, you're my hero. Okay, and here's another fellow. He says the following: "Time is a tool to record the temporal aspect of change." I like it because they come here, and they boast like, "Oh, you know nothing, but let me tell you what time is." And he says, temporal aspect of change. You look up temporal, it says, of or relating to time. So that's that for that. Yeah, these people never learn how to define terms. They don't think defining terms is important. And so when you criticize them on the basis of their definitions, they say, "Oh, you're doing semantics, Bill. You're doing word salad." They dismiss that because they don't like that their definitions are torn apart so easily, and they are. So yeah, it's very important to define terms in physics. Without that, without what I call the foundations of physics, without a set of definitions of the most important words you're going to use to give a physical interpretation, you have absolutely nothing. You need to know words such as object, distance, location, exist, motion, concept, space. You need to know how to define those terms. Then you can carry out a rational discussion with someone. But if you don't know what an object is, especially you don't know what existence means, what do you mean by exist? Does God exist? Does God not exist? I mean, then you can go on chasing your tail forever in circles. So yeah, you need to define words. Anyways, here we had in, what was it, 1911, I think it was. Yep, no, 1908. And this is Minkowski, and he said, "Gentlemen, the concepts of time and space, which I would like to develop before you today, have grown on experimental physical grounds." In other words, they did experiments, and they got these conclusions, and they said, "Oh, we discovered space-time." Okay? And henceforth, space by itself and time by itself shall completely reduce to a mere shadow. That's the death of time and space separately. And only some sort of union of the two shall preserve independence. So again, how do you merge space and time when space is static concept and time is dynamic? And of course, when you go out there, you don't find a definition for the word time, especially. Okay? Nobody has a definition to this day that you can sink your teeth in. They all eventually say, well, by the way, we don't know how to define time. We don't know what it is exactly. But we use it anyways. We use it in our equations, and we have this space-time where we merge time with space. They can do all those things, but they can't define the word time. And of course, they can't define space. They don't know what space is to this day. They say it's made out of particles that pop in from space, from the vacuum, from the void, right? And so space is made out of particles, it's a thing. Then they say it's infinite, like the numbers. And others say, no, it's not infinite, it's finite. And so we don't know if it's finite or infinite, if it's a thing or not. We have no idea. I mean, the mathematicians, they have no idea what space is. And so they're going to take this unknown called space, they're going to merge it with an undefined term called time. And they created space-time, and they say they proved it through experiments. Okay. Here we have good old Einstein. I showed this the other day. He took that space-time, he started warping it, saying that that's gravity for you. Okay? Mass bends space-time. Okay? And that's what compels mass to roll around another mass or around space-time. Okay, so this is what they did. They took this concept, space and time, merged it, and now they're starting to warp it. Okay? Think about that for a minute. It's like taking love and intelligence, merging them and saying, we're going to warp it now. Yeah. Okay, let's see how you do that. Okay, so what is actually space-time? Well, if you remember, for those of you who went to high school, right, you have what is called Cartesian coordinates. You have the x on the bottom and the y on the side, right? And so what you do, you use that to locate objects, like, you want to locate the position of something. You take, for example, an ordered pair, you take a number on x, could be a number 6. So you take 6 steps along the x, then go 5 steps upward on the y, and you end up at some point, 6, 5, and that's a location there on that coordinate system. Okay, very simple stuff that they teach you in high school. Okay, what's happened here is they've taken that, and that's what they turned into space-time. Okay, and here's a graphic representation of that I want to show you. Okay, here it is. You have the Cartesian coordinates. Okay, and you have x on the bottom and y on the side. What they did, they turned this into this space-time thingy, and then they started, warping it as well. That's what they did. Okay, so what you have here is a coordinate system. That's all it is. It's a mathematical system which they turned into a physical system. Okay, they simply went in there, turned it into this space-time canvas, fishnet, whatever you want to call it, trampoline, and then they put some weights in it. That's mass pushing it down, figuratively. Okay, pushing it down, and that's what the cause of gravity is. Okay, so what you have is really a Cartesian coordinate system that has been turned into this physical thing called space-time. Okay, it's a mathematical concept, especially the time part. The space, I don't know about that, because again, space belongs to physics. Space is not something related to numbers. Space is that black stuff out there, whatever that is. And so you have to point to it. If it's an object, you got to show what it looks like. If it's an object, if you present it as an object, so you got to show us the edges of space and label whatever's outside of it, so that we can get an idea, what is encapsulating space. That's if space is an object, a thing. And on the other hand, if you say space is a concept, no problem. That's what we say here as well. You have to define it. You have to define the word space. And we define it as that which has no shape. Okay? So it's not infinite, it's not finite, because infinite and finite are adjectives. You can only apply these adjectives to objects, to things. Space is not a thing. Space is the opposite of a thing. Space is nothing, that which has no shape. Therefore, it can't be neither infinite or finite. Okay? So that's our definition. But whoever gives the presentation, whoever thinks space is an object, has to first point to space and label space and whatever's encapsulating it. That's the way it works in science. Okay, we had the other day Mr. Augustine here, St. Augustine, and he created the notion of the block universe, which is, again, a synonym, really, of space-time. Okay, what did God do before he created universe? That's the question he was trying to answer, okay, because some people obviously asked him that question. And so he had this reasoning process. He said, God is not material, God is spirit. That comes from the Bible, right? God doesn't move, okay? God is, right, because if God is a spirit, God is a concept and therefore doesn't move. So far we're totally with him, okay? I agree here with Augustine, okay? Augustine, I call him, because he dealt so much with time. He says God is eternal. He's been there always. Why? Because he's in the present tense. He doesn't move. He's just in present tense, and that is as eternal as it gets. God is outside the universe. Okay, so the universe is something that's outside of God. God is going to create this universe. He created it and says time began when God made the universe. In other words, time is inside the universe, which is exactly what space-time is, what general relativity says. They say that space and time are within that ball that you see there, that flattened out ball there. Okay, God is outside. God doesn't move. God is really spirit, not a bearded guy like I put there. Okay, God is a spirit, so he doesn't move. He can't move because he's a concept. Okay, so far so good. How something that is a concept created a something that is an object, I don't know. Okay, that's something you got to explain the process there. But other than that, we have God outside the universe. God doesn't move. God is spirit, right? He creates this universe, right? And it turns out this universe has space and time within its borders. Okay? We call that the block universe, also known as space-time. Okay? So let's make sure we understand that. Okay? So general relativity did not come up with that concept, the concept of block universe. It was already there from Augustine in his Confessions. His book Confessions about, about 380 BC or something like that, AD. That's when he wrote it. I think it was closer to the year 400. Okay. Anyways, he wrote that book, Confessions. You can look it up. And here we see good old Brian Greene. And he's going to take the block universe, which he likens to a loaf of bread. He's going to slice pieces off of it. Each one of those slices is what? Time. Again, and I discussed the other day that you can't do that because time requires at least 2 frames of the universal movie, so you cannot slice it. You cannot have a single slice. A single slice, as Brian Greene is showing there, is really location. It is not time. Okay? Not motion or time. It's only location, distance, objects, space, and all static concepts such as existence. Okay. So here we have Mr. Stephen Hawking. What does he have to say? He's a guru, or was a guru until recently, of space-time. And this is what he has to say in his book, his famous book, A Brief History of Time. Einstein made the revolutionary suggestion that gravity is a consequence of the fact that space-time is curved. Space-time is curved? What do you mean? Or warped, right? He says, how can that possibly be if space-time is a concept? What do you mean it's curved or warped? Curved and warped are words that relate to physical objects. And good old Stephen Hawking, he's treating space-time as a physical object. And he's not the only one, as you can see up there, NASA. Okay, they have a picture of this. They show this space-time canvas, this fishnet, being warped by the Earth, okay, by the mass of the Earth, as so they say, okay. And the question is, here everybody's treating that as a real physical entity because they are talking about curved and warped concept called space-time. And so he continues, he clarifies, just in case you didn't understand, okay? Bodies like the Earth are not made to move on curved orbits by a force called gravity. The mass of the sun curves space-time in such a way that although the Earth follows a straight path in four-dimensional space-time, it appears to us to move along a circular orbit in three-dimensional space. So the Earth actually travels in a straight path, but that's out there in the four-dimensional world, you know, tesseracts and whatever. Here on Earth, we poor little creatures, we see it in us going around in a circle because we can only see up to 3 dimensions and no more. Okay, it says the mass of the sun curves space-time in such a way that although the Earth follows a straight path in 4D space-time, it appears to move along a circular path in three-dimensional space. Okay, in general relativity, bodies always follow straight lines in four-dimensional space, but they nevertheless appear to us to move along curved paths in our three-dimensional space. He says that in his book. Here you have a guy who studied at least 10 years at the universe, and he says this nonsense. Okay, not only does he treat space and time, both which are concepts, he treats them as a physical object. He warps them, he curves them. He's going to put the Earth there, and he's going to say, well, the reason it goes around the sun, it actually goes in a straight line in four-dimensional space, but here in our world we see it as a circular movement. Totally crazy. I mean, I don't know about the four-dimensional. I mean, I haven't drank the 10 beers that Hawking drank. You know, maybe that's what made him see these visions. All we see here is that, you know, the Earth goes around the sun in a circle, more or less, right? And the question is why? And they say, well, the reason it goes around in circles is space-time is curved. In other words, time is curved, and there's this wall. That's what they're showing, that's what they illustrate, that's what they explain. There's this wall of time that prevents the Earth from flying out of the solar system. Curved time. So you figure that out, okay? And just in case, you might say, well, Bill, maybe you misunderstood. Here's NASA, okay? NASA, this is from their page, okay? NASA's Gravity Probe B, a little rocket they sent out there with some gyroscopes, to test whether the gyroscopes would drag space-time around itself. Again, treating it space-time as a physical object. Okay? It says Gravity Probe B mission has confirmed 2 key predictions derived from Albert Einstein's general relativity, right? Which the spacecraft was designed to test. Okay, the experiment launched in 2004 used 4 ultra-precise gyroscopes to measure the hypothesized geodetic effect, the warping of space and time around a gravitational body, and frame dragging. You know, they're going to drag space-time around, right? The amount a spinning object pulls space and time with it as it rotates. It's pulling on on time. How do you pull on time and drag it around yourself? Jesus Christ, what are these people talking about? And we spend money, you know, taxes and so on, paying for this whole thing, okay? Gravity Probe B determined, it's already been proven, right? Both effects with unprecedented precision by pointing at a single star, etc., etc. Okay, so what are they saying there? They used Gravity Probe B to drag space-time around itself. It's dragging, it's pulling on time. That's what they're telling you. These are people who have at least 10-year degrees, PhDs, and are telling you this nonsense, this poppycock, that a gyroscope is pulling space or time, both space and time, but specifically time, because I think that's straightforward. I mean, how do you pull on time? How do you pull on a second? Okay, that's what they're saying. Okay, and someone explains also over there at NASA, says time and space, according to Einstein theories of relativity, are woven together. They're woven. Someone, I guess God wove them together, yeah, used maybe the rope hypothesis, the rope to do this, forming a 4D fabric called space-time. They're talking about a fabric. What's a fabric? They're talking about, you know, some kind of shirt, maybe a dress. You know, they're talking about something. Okay? The mass of Earth dimples this fabric, much like a heavy person sitting in the middle of a trampoline. Okay, so I think you're getting the hang of this. It's not that I'm coming up with all this. These people are telling you in your face that there's something called space and time. You drag them around, you can sit on it, and when you sit on it, you push it downwards. Gravity, says Einstein, is simply the motion of objects following the curvaceous lines of the dimple. If Earth were stationary, that would be the end of the story. But Earth is not stationary. Our planet spins, and the spin should twist the dimple, slightly pulling it around into a four-dimensional swirl. So now the Earth twirls around, and it's going to pull on space and or time, right? This is what GPB went to space in 2004 to check. Put a spinning gyroscope into orbit around the Earth with a spin axis pointed towards some distant star as fixed reference point, okay? Free from external forces, the gyroscope's axis should continue pointing at the star forever. But if space is twisted, okay, space, nothing is twisted, okay? The direction of the gyroscope's axis would drift over time. By noting this change in direction relative to the star, the twists of space-time could be measured. My dear God. You know, when it comes to it, I'd rather go back to the old-time religion than the new-time religion. This stuff is beyond me, okay? They're warping time. They're pulling on time. They're sitting on time, weighing it down, curving it, and that causes little balls like the Earth to go around in circles forever. That's their explanation. That's their physical interpretation. And of course, when you point that out to them, they say, well, we don't understand it either. And by the way, you're bringing up a subject that belongs in philosophy. We just do equations. We don't do physical interpretations. So why did they even try? Why did they even attempt a physical interpretation if it's not part of their job description? Well, very simple. Because if they didn't, all their math would be worthless, which it is. Okay? Because all their math is leading them to conclude something about the universe that ain't so. And that is how it works. And it doesn't work the way relativity says, with space-time and time being warped. It doesn't work that way, believe me. Okay? So this nonsense that they have that you can warp time, that you can warp space, which is nothing, you know, how do you do that? You know, grab a piece of space and show me how you warp it. It's very simple, you know. Okay, but he doesn't stop there. Hawking continues because he says, look, if space-time is warped, right, guess what happens to light when it tries to travel? Well, here you have a zigzag of light. Again, the fact that space is curved means that light no longer appears to travel in straight lines in space. General relativity, what predicts, we're going to talk about that today with our science critic, right? Predicts that light should be bent by gravitational fields. So there you see how it's warped. Okay. Now he says it should be bent. I don't know how you can bend light when they say it's made out of photons. You can at best talk about deflect and deflection. You deflect a series of photons, not bend. What are you bending? Are you bending a photon? I mean, what are they talking? They don't even have their language correct. Okay. But yeah, is that how light travels in like a curve around the sun and then around the earth and so on? Well, I don't think so. You know, light always travels straight. Rectilinearly, it's called. Okay, and what are some of the other conclusions that Mr. Hawking comes up with? He says, before 1915, space and time were thought of as fixed arena in which events took place, which was not affected by what happened in it. Bodies moved, forces attracted and repelled, but time and space simply continued unaffected. It was natural to think that space and time went on forever. Space and time are now what? Dynamic quantities. When a body moves or a force acts, it affects the curvature of space and time, meaning that they move, and in turn the structure of space-time affects the way in which bodies move and forces act. This fellow is saying that space and time move, okay? So it's not only bodies that move, but space and time move. And I'd like to, ask his bartender to give me the same stuff he had. Jesus Christ. Okay, and then he says the following, says, the old idea of an essentially unchanging universe that could have existed and could continue to exist forever was replaced by the notion of a dynamic expanding universe, meaning, you know, what's expanding? Space, right? And I guess time as well, because time is expanding, right? That seemed to have begun a finite time ago, and that might end at finite time in the future. The revolution was to be the starting point for my work in theoretical physics. Okay, great. What did you find out? Roger Penrose and I showed that Einstein's general theory of relativity implied that the universe must have a beginning. Okay, so there's the beginning, You know, a little explosion there called the Big Bang, and from there we have this bottle, or I guess a glass. Sometimes I put some beer in it. Okay, I guess it fell on its side, but that is your space time there. There's the time is going rightwards, and I guess space um, is inside each one of those frames, each side inside each one of those cross sections or slices, as Brian Greene illustrated. He sliced them apart. Right? Okay, so what should we conclude from all this? Well, this is what space-time is. It started out as a coordinate system. Okay, what they did was replace width with space, and space. The three dimensions of space are there in a single axis, and then they arbitrarily replaced the axis of height with time. Okay, so we have space on the x-axis, time on the y-axis. From there, they kind of turned that into space-time, and then they started warping it. So what are they warping? They're warping this concept, this coordinate system created or originated by René Descartes, okay, 17th century. Okay, so this is what it's all about. What you're warping is this concept, and that's what these people deal with every day. They talk about space, time, and then of course they're going to put in there black holes and wormholes and dark matter and dark energy, and they're going to fit it in that space time. It's part of that space time. Part of it is these other things that they've created over time, right? So we have space and time coordinate system that's been warped, and they're going to be putting these other entities, which are mathematical concepts again. They're going to fit them in there to explain, especially gravitational phenomena. That's the point of it all. Okay, so why doesn't the Earth fly out of the solar system according to general relativity? Because of space-time. You have warped time. There's this wall of a warped canvas, so to speak, a warped fishnet, and it's that warpage that creates a wall, so to speak, that prevents the Earth from flying out of the solar system. The funny part is that, you know, the Earth is not allowed to go outwards, but, you know, we're at the edge of the Earth there, and I don't feel squashed by this wall of time. So I don't know why the warp wall of time does not squash us. Okay, that's something that they would have to explain, because it can stop the Earth, right? Because the Earth is banging up against the wall, right? It's sliding or rolling along this wall, but we're at the edge of the Earth and we don't get squashed. So I don't know. You figure that out. How it is that the Earth can roll around time, warp time. Warp time is strong enough to prevent the Earth from flying out, but it's not strong enough to squash you against the the ground of the Earth.